Lecture 3.2, Differentiability. We have 4 vacation slides today of Arches National Park in the state of Utah. This first scene is an area called Park Avenue because it reminded people of the tall buildings on Park Avenue in New York. This slide is called North Window Arch. Notice the people in this picture to give you a sense of scale. Our next picture is called Balanced Rock. And finally, the famous Delicate Arch. To be differentiable, a function must be continuous and smooth. Derivatives will fail to exist at a corner, such as this graph of f of x equal the absolute value of x, at a cusp, as in this graph of f of x equals x to the 2/3, at a vertical tangent, as in this graph of the cube root of x, at a discontinuity, such as this piecewise graph of f of x equals -1, where x is less than 0, and 1, where x is greater than or equal to 0. Most of the functions we study in calculus will be differentiable. Derivatives on the TI-nspire. You must be able to calculate derivatives with the calculator and without. Today you will be using your calculator, but be sure to do them by hand when called for. Remember that over half the AP exam is no calculator. Example, y equals x cubed. Find dy dx. We input d dx x cubed and press enter, and the calculator returns 3x squared. In case you've forgotten, the easiest way to find the derivative template is to use the keyboard shortcut Shift-. Example, y equals x cubed. Find dy dx. So we enter into the calculator d dx x cubed, which returns 3x squared. We find the derivative template by pressing Menu, 4, which is calculus, and 1, which is derivative. To find the derivative at a point, for example, x equals 2, we can do this. Press Menu, 4, calculus, 2, derivative at a point, and this screen appears. Insert the variable x and the value 2 in this case, and then press OK. Now we have the partially completed derivative template. We just need to insert the expression in the blank and then press enter, and the calculator returns 12. Another way we could accomplish this same thing is we could also create this same expression by finding the vertical bar symbol at control equals, which might be a little more straightforward and easier to remember. Warning: the calculator may return an incorrect value if you evaluate a derivative at a point where the function is not differentiable. For example, the derivative of 1 over x with respect to x at x equals 0 returns negative infinity. The derivative of the absolute value of x with respect to x such that x equals 0 returns plus or minus 1. In actuality, in neither of these cases is the derivative defined. Now let's look at graphing derivatives. First, let's graph the function f1x equals ln x. So here we have the graph of ln x. Now graph the derivative. We have f2 of x equals the derivative with respect to x of ln x. And we find the derivative template most easily by using the shift minus sign shortcut. Now this graph looks familiar. This looks like y equals 1 over x. If we use our calculator to evaluate the derivative with respect to x of ln x, we do get 1 over x. However, the derivative of ln x is only defined for x greater than 0, even though the calculator graphs negative values of x. Two theorems. If f has a derivative at x equals a, then f is continuous at x equals a. Since a function must be continuous to have a derivative, if it has a derivative, then it is continuous. The intermediate value theorem for derivatives. If a and b are any 2 points in an interval on which f is differentiable, then f prime takes on every value between f prime a and f prime b. In this example, f prime a equals 1/2. That's the slope at point A. F prime b equals 3, which is the slope at B. Between A and B, f prime must take on every value between 1/2 and 3. As the slope gradually increases, it must take on every slope between 1/2 and 3.